Oh, okay, yeah. Two questions. Please, is exam going to be difficult? How much time does a normal student study this class? Well, good question, but I might be objective against this question. So normally if you really understand the material for this class, you wouldn't have any issue for getting a very good grade for the exam. I don't really can tell how much students would study for this class. It really is subjected to how much background knowledge they have on cryptography. So that would be really depend on you. I am not taking attendance for this class. So meaning that, people can either join the class or they could be offline. We would have the videos of these lectures on this platform, and then you can access them and try to go through them again, maybe before the exam or anytime you have questions. But really, it's gonna be really depend on you. It does have some math, so it is not a super easy course. I compared this course with my other course of network security. Comparing to the network security, yeah, it is a little bit more difficult because we have more math and more things are involved. It is really of your choice, for saying if this is going to be difficult or it's going to be easy. Okay. Did I answer your question? Speaking of the objective of cryptography, so the very first thing that would cross your mind is secrecy. So the secrecy, which is, we can discuss it in two different parts, which is privacy and also at the same time confidentiality. So the goal of both of them are that the data should be protected against unauthorized access. So if you go back to the first slide, we had Eve here that, Alice is sending some message to Bob. And one of the objectives here is that we want Eve, that is an unauthorized user over here, to get to learn what is message M. The only authorized message here is Bob because this message is intended for Bob. So in this case, the goal of the cryptography is something that you always have thought about, is to ensure the confidentiality of the message. We also have privacy, that, some other topics we might start to cover privacy. And in terms of privacy, sometimes you want to use cryptography to control who and how can access what information and what they can do with that information. So it is a little bit more complicated. And if you can imagine, it's sort of a access control in some sense, but in another sense, when it comes to what they can do with it, you can control. When somebody accesses the data, you can't tell what they can do with that data. So it is a little bit more complicated than just confidentiality. But overall, the notation of privacy wants to put you in a place that you can decide who can access what information and what they can do with that information. And we will have objects of cryptography kind to enable you to control that. But I think we won't be much covering those in this course. But when we get to secure election system, when we design it and we prove the security, then we would start to discuss some about the privacy and how that scheme or that protocol would ensure the privacy of the users. When the right times comes, we would have even better discussions. The second thing that cryptography, as a goal of cryptography, is the integrity. So we said that Alice is sending a message to Bob. So very well, we use encryption, for example, and we make sure that Eve or somebody else can read this message. But what if somebody replaced that message with something else? What if somebody modified the message? A better example is that when you are downloading, let's say, a file from internet, when you're done downloading the file, you want to make sure that nobody or not any of those bits of regarding to that file has been flipped during the transmission. There are some CRC code, error correcting codes and different things like that with information theory that the basic TCP/IP protocol would use to make sure that the packets that you receive are error-free and they are meaningful. But integrity here is way more advanced thing, and sometimes the data could be altered, or the noise can change the data, let's say, and the CRC codes are unable depending on the number of the bits that has altered. But the integrity check on cryptography is a very strong algorithm or objective to make sure that not even a bit of the message has changed, at least with a very high probability. So this is a very interesting thing that or objective of cryptography that we would start to discuss together. It doesn't just end there. Sometimes you heard about, for example, digital signatures, that when you write a check in a physical world, you have a check is a piece of paper, you say, I want to give this amount of money to this person, and you sign it. So the only way that the bank can verify that this check is valid is to see your signature and matches your signature against what they have in their system. Or maybe in Taiwan, you guys use the stamps. So it is very important that you use the right stamp. It happened to me that I lost my stamp many times, and I happened that I find them later on, and I accidentally used the old one for some of my documents, and of course that becomes some issue. So I had to go to the bank and do some process to change that old stamp to the new one, and vice versa. So it is the same thing, but that stamp or your signature is the thing that would verify the integrity, the correctness of that piece of document that is a check. But now imagine that we want to replace that with some algorithm that somebody can maybe forge my signature on a check. If you get a new blank check, maybe you can forge my signature, and you've seen on movies that some people, they have those skills. But when it comes to cryptography and we use digital signatures to sign a check, then that becomes very difficult, because the signature is not just a picture or a sign on the document. It takes all the bits of the document and do some computation, and leaves the result of that computation on the document, on a digital document. And it is very computationally hard for another forger to, let's say, forge the check, a new check, and would be able to provide a correct signature. And therefore the security of the digital world, the digital checks, are much higher than those physical and the traditional ones. So again, I think good amount of advertisement for integrity goal for cryptography. Let's just move on. The third one is authentication. So you have heard about authenticating a document or things like that. We break it down into two things. The first thing is data origin authentication, and the second one is entity authentication. So the data origin authentication, we want to verify that the origin, when you receive a file or receive a message, you want to authenticate the origin of the message. So if I go back to the first slide, Bob received a message and it says Alice, but now that Bob has received this message, he wants to make sure that this message indeed comes from Alice, not from Eve, maybe. So data or region authentication would help Bob to go through some process with Alice, and or maybe Eve, that maybe Eve is impersonating himself to be Alice. And in that case, Alice would be able to verify that, okay, this is indeed me, and therefore Bob would conclude that, okay, the message that is coming is from Alice, and okay, I accept that. But maybe when Bob would engage to that communication with Eve about authentication, Bob would not get convinced, and if this message, Eve sends some other message to Bob, Bob would just drop that message and says that, okay, I don't think I can trust you to be Alice, so therefore I'm going to ignore this message. And then the second part is that, sometimes it is very important for both parties to prove to one another that who really they are, or they are really who they claim to be. And that's where we would use the notation of entity authentication. So both parties, they want to know each other. So why do we have two different notation? Why we don't do entity authentication all the time? So it happens that, for example, when you connect to gmail.com, let's say google.com or some other web service to consume some service, normally the web service, let's say, is a publicly available web service, and you don't have a username and password. You don't require to have username and password. So in that case, the only thing that you care is that the web service is the right web service that you're connected to, and it's not a malicious web service. So in that case, you want the web service to prove that it is indeed the web service. So in that case, it is just one-way proof, right? You don't have to, the web service wouldn't challenge you that, okay, you also need to prove yourself that you are an anonymous user. Well, you don't have to prove yourself. If the server wanted you to prove yourself, the server should have asked you for some credentials, right? For example, when you go to gmail.com, then the first thing that your browser would do is to verify that your authenticate the Gmail server, that you are connected to the right server. And once that is done, then the server will start to authenticate you. And that is the moment that you see that enter username and password page, because server wants to make sure you are who you claim to be, right? So that is an example of entity authentication or both side authentication. Both parties want to know that they are connected to the right. Both parties authenticate themselves and they are really who they are. So in crypto, these three first objectives are very important, and we normally would use a very important thing to remember them. And if you just take the first three letters of them and put them together, they would make you CIA. So if you happen to see some movies, you have heard about CIA. This is not that, the CIA in the US that we're talking about. This is confidentiality, integrity, and authentication. These are the three most important objectives of cryptography. But I think when we put them together like a famous name, it would be easier for you to remember them. So if somebody asks you what is the objective of the cryptography, you would say it is a CIA. It is confidentiality, integrity, and authentication. There are other objectives, that they come and go depending on the time and the application that you are working on. And one of the most important one is non-repudiation. You would have some good examples to go through this one. And you know, sometimes in some system it happens that you ask for something and then later you deny. For example, you've seen in some movies that, you know, some employee would make some transaction because the boss asked the employee to do something, and then when, you know, the whole thing fails, then the boss comes back and says, well, I never asked you to do this in the first place. Well, because, you know, it was an order or request or a task that came out of the mouth or in verbal one. So there's no proof. So the poor employee now cannot prove that, oh, okay, I did this because you asked me in the first place. But since it was all a conversation and verbal, so there is no way for the poor employee to protect him or herself in this situation. So this is a very specific one, and sometimes we have it in some systems that we would want to have them. So sometimes we can add the objective number 4, and that is a non-repudiation. I think we would have some examples. I don't want to expand more on this. I think with your example, it would be easier to understand it. All right, so with that being said, let's go and, you know, elaborate a little bit more about the secrecy part. So most of the time, you know that when we are talking about the secrecy, which is confidentiality, we have the way that we can satisfy that objective is to use a crypto system, encryption, decryption crypto system. So this encryption and decryption crypto system come with normally 3 pieces of algorithm. One is encryption algorithm that is denoted by E, and then decryption, and also most of the time a key generation algorithm. And I should add that one here. That is key gen, right? Key generation algorithm. Besides that, you would choose a key from a subset of available key. That this key is a capital K is a subset of all keys. And then when you choose a key from that set of keys, we normally refer to that choosing key to be a small k. So just notice the notation over here. So we have again a message that comes from a space of message, and also the ciphertext. It comes from the ciphertext space, so capital C and capital M. So the encryption algorithm would take a message M and a key that is chosen, and then transform the message M to another piece of information that we call it ciphertext C. So that is the goal of the encryption algorithm. And the goal of the decryption algorithm is to take the ciphertext, the transformed message, decryption algorithm, and the same key, and then he would convert it back to the same message that we sent in the first place. So how does this work in a practice? So let's go and make it easier to understand. So suppose we have, give some here to it, Alice, and then we have Bob here. So Alice wants to send a piece of information now to Bob, but she doesn't want somebody like Eve over here to be able to learn what is she sending to Bob. What she would do is that she would compute encryption. She passed the KK and then the message M, and this would become the ciphertext C. Instead of Alice send the message itself, then she's sending the ciphertext C along the line. Now Eve can see the C, and Bob would receive it. This key is a key that has been shared only between Alice and Bob. Okay, only Alice and Bob got this key. So when Bob received this message, what he would do is he would compute the decryption of the same key and the ciphertext that received, and he would recover the message M. And then over here, what you could see is that Eve cannot do this one because Eve wants to run the same decryption function, but he doesn't know what is the key, right? But he knows the C, but then he doesn't know, the actual message that was transferred, right? So this is, if I wanted to show you in pictures, this is what is happening. So instead of Alice sending what we call it a plain text, she computes the ciphertext using the key that she shared with Bob, and she's transferring the ciphertext to Bob, right? And Bob is the person who happened to have that key, and they shared it some time ago. And since Bob and Alice are the only one who know that key, and they have not shared that key with Eve, so again, Eve has Wireshark, and he's capturing anything that is being sent and received between Alice and Bob. But now that he sees the ciphertext, and he knows that they are using encryption, but he knows the algorithm D, he knows the ciphertext, but since he doesn't know this key K, then he is not able to recover the message M. Later on, we would discuss how hard it would be for, or it would be almost impossible for, or I should use a better word. The probability for Eve with not knowing this key K to be able to recover this message would be very low, okay? And later on, when we discuss different algorithms and we compute that probability, then you will see that that is almost impossible. Okay, so now that we have a common understanding of how this algorithm and the notation works, so we have another notation, another thing for the correctness of this algorithm. So we can't just use any E and D, any encryption and decryption algorithm. We want to use an algorithm that for all key that we instantiate from this capital Z key, if we decrypt the message with that key, and then let me write this one fast. So what this equation is saying is that if this is a correct, encryption and decryption algorithm, for any key that you take from this subset of this these keys, and for any message that you take from the subset of the allowed messages, if you encrypt that message with that key and then decrypt it, you should get back to the same message, right? So this is just to make sure the correctness of our crypto system. Remember, you can have a crypto system algorithm that, with some keys it works fine, but with some other keys it doesn't work. That cannot be an encryption-decryption algorithm. Okay, so that is thing to remember. So I think, yeah, we have discussed the first one. So so one of the examples of yeah, so far I think what we've discussed is we call it symmetric key, because both sender and receiver would use the same shared key to do encryption and decryption. So somehow, sometime in the past, or with some algorithm, we have shared that key K between Alice and Bob, or maybe Alice and Bob, they met each other the first day and they agreed on a key. And when they go online, they always use that key to, send and receive messages. And that's the reason that this algorithm is working. And because both parties use the same shared key, we use them, we call it symmetric key. One of the very old and ancient way of encryption is Caesar shift cipher. It is I think it is like for at least 2,500 years ago. And back then they would use, for us now it sounds that it is very naive, but back then it was a very good one. So the way that the encryption work is that you can choose a key, and the key is anything between 0 to 25, the value. And then we also know that in English alphabet, we only have 26 letters. Let's forget about the capital and small cases. So we can map every digit to a letter, right? So A to be 0, B to be 1, and so on and so forth. So back then they thought that, okay, maybe this could be a good thing, so that we can choose a key from 0 to 255, so 25, which is a character. And then when they wanted to encrypt a message, they would go through a character by character, and then they would just add the key. For example, if the message to be sent was ABC, and then let's say this is the M, and then let's say the key is 1, which is, by the way, it is look like the letter B, right? So in order to encrypt this message, so what they would do, encryption of ABC using the key equal to 1, what it would look like is that you're adding digits. So we know that A is letter 0, this is 1, this is 2. So the output is that it would just add the key, so it would become 1, and then 2, and then 3, right? So we are literally sending, in a sense, we are sending B, C, and D, right? Of course, there is a modular operation, but since our key is very small, it doesn't really get engaged. So you see that they have substituted ABC with BCD. It is not a very strong one, but it was something that was working back then. So you see that modular 26 is to make sure that we would never get numbers beyond 0 to 25. It is a circular set, and everything would basically land there from 0 to 25. And the decryption is very easy. As soon as you have the key, you would just go and do the subtraction, and then you can decrypt the message, so you can get back to the same message that you sent. And just wanted to share with you that this is one of the very old crypto systems. And suppose that both sender and receiver, they knew the key K. So maybe both of them know that key is 1 here, or key is 10. And then when they would encrypt the message, the other party would be decrypted. But there are a lot of problems with this crypto system. Anyone wants to bet what do you think is a problem with this crypto system? Do you think this crypto system is safe? Oh. So let me get to this question. I will get back to your question very soon. So anybody wants to discuss any idea? What do you think is wrong with this crypto system? Limited combination. Yeah, very good. So key can take only from 0 to 25, right? So nothing would stop you to try all the possible keys, and then you will be able to break it, right? In the worst case, by trying 26 different keys, you are able to break any of this, messages, right? There are a different number of issues again, one of them, so it is brute forcing. If you do not want to brute force, There are other methods called statistical analysis. In a statistical analysis, what you would do is that you know that some of the words, some of the letters in English, appear with a higher frequency than the other ones. For example, E, A, I, O, the vowels would appear way more than other letters such as X, Y, Z, So somebody can go and do those kind of statistical analysis and find that, okay, in here, if, for example, the letter A or I are very probable, with this kind of encryption, because you always add a number to I, so you change it to another constant. And whatever other constant letter you change it to, you're adding you're moving the probability of I to some other character, let's say H. And now if you see a lot of H, you would see that, okay, that might be I or A or, one of those vowels, because H appear a lot. So it must be one of those. And that could actually help you to not even want to run brute force, and you can break it even faster. Yeah, again, so occurrence of a specific alphabet. That is, in general, we call this, what you name here, we call it a statistical analysis. A good crypto system should be able to hide those information. If some letter or some symbols in your message are repeating a lot, it shouldn't be the case on the ciphertext. Or let me put it in a different way. Let's see your message in a binary format. And if the number of ones in your message is more than number of zeros, it shouldn't be the case for your ciphertext. A good crypto system should have, most of the time, even number of zeros and even number of ones, if you look at the ciphertext and message in a binary format. So, it is not very important to discuss here. And just like, getting you guys ready to see how easily we can break some of these crypto systems, and at the same time learning some of these techniques that how to break a crypto system. Now, knowing these two techniques that you've just discussed, one was brute force, and the second one was a statistical analysis. So the first thing that you learn now, even letting me to get to the material, is that the key space should be large, right? Otherwise, if the key space, just like this algorithm, is, let's say, 26 letters, then nobody would stop you to just write a for loop with 26 checks, and you are able to break it. So you have to have a key space that is much larger, and you can cover it with that, for loop easily. There was a question. For authentication, is there another kind of need to verify the receiver side only? Yes. So sometimes we call it server-side authentication or mutual authentication. So if you're saying receiver, in this case, sometimes we have service consumer and service provider, right? Sometimes, let's say you want to connect to gmail.com. I think the best practice is that before you handing your username and password, you have to make sure that you're connected to the right server, and that is being done with your browser. That we would use a TLS to do that authentication, and then you see that green sign on the top of your near your URL, the lock. That means that the server has been verified, and then you enter your username and password. I think what you're asking is that what if you don't care where you're connected to, and only the recipient, which is the service provider, wants to authenticate you? Yeah, you can do that. We call it one, server-side authentication, or both side authentication, or entity authentication. So it can happen in any direction. Either one side would authenticate the other party, or both parties want to authenticate one another. So depending on the scenario, you could choose which one would make more sense. Okay. So given that, I think now we've been discussing about symmetric key cryptography. And now let's see how does that look like when we go to public key cryptography. In a public key cryptography settings, it is a little bit different. Both parties, they do not need to, meet each other in the past. They can just use a different, scenario to communicate, even without having that common key K. And, in a lot of scenarios, it happens that, you want to connect to gmail.com. You've never walked into the Google office and asked them, hey, let's share a key. And then when I go home and I want to connect to your server, then we know what key we use, right? It doesn't happen in the practice, because in a practice, we use a different sort of cryptography that is called public key cryptography, or it is asymmetric. Unlike the other one that it was symmetric key, that means that both parties use the same key. Now we use asymmetric, that every party would have two keys. So imagine the world now that every party would have different keys. So I'm again using Alice and Bob, but you can imagine that Alice is your browser and Bob is maybe gmail.com. So Alice and Bob. Before anything gets started, Alice and Bob would go ahead and generate their keys. So every user, we say that they have two keys. So Alice have the public key of Alice, and then the secret key of Alice. Bob also got that. The public key of Bob, and then the secret key of Bob. Okay. There is a correlation. There is a mathematical relationship between the public key and a private key. It is something that we will discuss it in the future. But when we are talking about the public key infrastructure, normally we would also introduce a repository where every user would store their keys there, the public keys there. So this is they would publish the Alice public key, the Alice, the PK of Alice, and also let's say the publish. This is the one, and this is the key. So let's say we would use the binary notation 1 0 1 1 0, so on and so forth. This is the binary representation of the Alice public key, and then similarly for Bob, okay? So it would be different. So the story here is that every user, they will, after they generate their public key and their secret key, they go ahead and publish their public keys into some publicly accessible directory, so that every user can go ahead and download these keys, these binaries. But they would keep the secret keys secret, and they don't publish them. They just keep them private. Okay. So the first thing to know about them, so once they have done this, is that there is a mathematical correlation, as I said, between the public key and the secret key. It is a place that we mentioned that it is mathematically hard for somebody to just have the public key to be able to derive the secret key for that user. Why is it so? Because we said that every user should publish their public key to a public directory, publicly accessible directories, meaning that everybody can see this public key of Alice and Bob. Just knowing this, it is impossible to derive their secret key. So their secret key that they didn't share would remain safe with them. And then Now that they want to use this public infrastructure, it's going to be interesting. So in order for Alice to send a message to Bob, she would do this one. She would decrypt a message with the public key of Bob and put that message here, and then would get this one to be the ciphertext. And Bob would receive this message. I'm sorry, would encrypt. I'm signing the message. And Bob received this message, and what he would do is he would decrypt this one. So he would decrypt this message. See, using the secret key of himself, secret key of Bob, and then this pass the ciphertext, and then he would be able to recover the message M. Just like before, Alice was able to send a message to Bob, and Eve is here again. Eve would only see the ciphertext C. Eve as well wants to try to decrypt the message, so Eve would try to decrypt it, so he knows the C, but he does not know the public key of Bob, and therefore he doesn't know how to recover M. But what we've done was that Alice wants to send a message to Bob. Alice will go back and check into the public directory, find the public key of Bob, use that to encrypt the message that she wants to send secretly to Bob. And she would encrypt it. Because of the mathematical relationship between the public key and the secret key of the Bob, and the Bob is the only person who has the secret key for this public key, he is able to to recover M from the ciphertext. But Eve cannot do that because of many reasons. One, Eve doesn't know the secret key of the Bob, and Eve, by just knowing the public key of the Bob, we said it is hard to derive the secret key. So Eve wouldn't be able to decrypt this message. So again, Alice was successfully achieved her goal to send a private message to Bob. But as you could see this time, she didn't have to share a key with Bob like before, right? She just used Bob's public key to, encrypt that message and send it to Bob. And interesting enough now, if Bob wants to send a message, reply that a message to Alice, Bob would be able to do the same thing. Bob would go and find Alice's public key, and he would be able to encrypt his message with Alice's public key and send it to Alice. And this conversation can go on and on. So I think the story that we've learned here is that we can achieve the same thing with two ways. In one, we have a symmetric key cryptography where we assume both parties they share a key. But now, with the use of the public key, we can achieve the same thing, but without the users to have a pre-shared key. And I think with the example that we just gave, I think now it is understandable that why this is a very interesting topic or interesting breakthrough. And the reason of that is because, unlike, if you forget about this dating, if you talk about Alice to be a user and Bob to be some major server, you can go to, for example, Google offices in a city and ask them, hey, let's share a key, when I go home, I want to connect to you. That could be very hard. But now, with the help of public key infrastructure, now they can achieve such a communication without even seeing each other before. And this is possible by just using the public key, which is asymmetric crypto system. And I hope that now you have a better understanding of why sometimes you want to use public key and sometimes not. Speaking of efficiency, asymmetric or public key cryptographies are way slower than symmetric ones. For example, RSA is an example over here. So we can have, for example, RSA, and for the previous one, when we define the algorithm, we could say, for example, here could be AES, right? So AES is many times faster than RSA. So that is the reason that, you know, we don't use RSA to encrypt a large file. You know, we would use RSA to share a key, and then we use AES to, you know, encrypt a large file and things like that. So I'm bringing this example to let you know that it doesn't mean that since public key is very easy to use, we do not use the symmetric key. No, the answer is that these two you know, trends of cryptography, they would complement each other. We normally use public key to share a key, you know, and then once we share a key, we go back and use symmetric key, you know, something like AES, to do the encryption. And the reason for that is that AES is many times faster than some public key cryptography such as RSA. And it doesn't mean that, you know, symmetric key is not worthy to investigate anymore and we should only focus on the public key. The answer is no. We need both of them to be there for us to be able to have a very secure and efficient communication. All right. Any questions so far?